Hello maths fans, Dr. Tom Crawford back to continue our lecture series on mathematical modelling in sport. Just as a reminder, or in case you didn't see the first lecture, I am one of the maths tutors at St Edmund Hall, which is another one of the Oxford colleges, and I also run my own YouTube channel, Tom Rocks Maths, and also my website, tomrocksmaths.com. So there's loads of additional resources for you there to look at investigating maths and science in general. So in our first lecture, we looked at modelling penalty kicks and how we can use Pythagoras' theorem and quadratic equations to try to work out the perfect place to aim our shot. What we're going to do in today's lecture is look at lines of best fit and a little bit of statistics. So what we're going to look at is the men's marathon world record. We're going to look at how it's changed over time, over the last 110 years or so. And then we're going to try and construct a line of best fit and then possibly use that to make a prediction into the future about when the world record will go below 2 hours, for example, and also maybe what the limit might be for the world record. Because whilst we've seen in the past world records starting to decrease in running events, it seems sensible that at some point it must flatten off. There is a maximum possible speed or a minimum time to run these particular distances. So perhaps we can use maths and our lines of best fit to try and figure out what's happening there as well. So our starting point is going to be to look at the data. So the graph of the men's world record for a marathon over the last 110 years. So since records began. And I'm going to draw a rough version on the board so that we can talk about this and I can draw it and annotate it. But I will also put a more detailed version on screen so you can see the exact data set for yourself. So it goes back to 1910, I believe, is when we have the first records around that kind of time. I'm going to go all the way forwards to the end over here, which let's say that's 2020. And of course, it could continue into the future. Now, what we see on the y-axis, this is the year. I should say this is the year. And obviously we're starting at 1910 rather than 0. And on the y-axis, this is going to be the world record for a marathon. So this is the world record. And the world record back in 1910 was about 3 hours, as you'll see in the accurate data set. So if I mark this as 3 hours, and then present day, it's just over 2 hours. So if I say this bottom line here represents 2 hours, of course, you could go below, it could continue down, but we're just going to draw it at 2 hours. And then somewhere in the middle would obviously be 2.5, etc. So this is our approximate axis. So I could fill in the gaps, but I'll just leave it like this. Again, you can see the real version as well. Now, back in 1910, so what happened here was there were quite a few records very quickly after each other. Very, very quick decrease initially. And this is because it was suddenly announced that we were going to start keeping these records. So people had been running marathons before and probably running them faster than some of these original first few times. But at the point when you start keeping records, the first person to run the distance after that point will actually set a world record. So there's what we call an adjustment period. So once you start recording records, the first few will sort of very quickly begin to decrease until they start to settle on what's actually the fastest time at that particular point. So as a potentially silly example, if I decided to start recording the time it takes to do a lap around my flat where I live, then the first person to do it, me, would set the world record. But then if an actual runner, somebody who's much faster than me, comes along and then they ran a lap, they would do it faster. But at some point, I would have held the world record initially because I was just the first person to do it. So there's this adjustment period here at the beginning until it settles on what's the actual record. And then what we see in the data, again, this is just a sketch compare it to the real one, it's just going to have the same kind of shape. We start to see it come down a little bit, and then sort of around sort of here, if I label this as 1940, what we see in the 1940s is there's a bit of a gap. Now, some of you can probably think, or if you look back through history, what happened in the 1940s. Of course, we had World War II, so obviously other things were happening that weren't running marathons. So there was a pause in the races, and therefore records just weren't kept during that period. Or maybe people just weren't running because, again, other things were happening that were taking over what was going on in the world. So history actually plays a really important role in this record keeping and what is a graph and a mathematical picture, if you want. So there's a gap for the World War. Then it starts to come down again. That's what we see. And then sometime around 1970 or so, it starts to go flat. So it starts to kind of tail off. So there's a few records, but whereas here they were kind of coming down and then here they were coming down, it starts to go quite flat around the 70s. Now, I'm not sure I really can completely explain why. One possible theory is that up until this point in history, you kind of, there wasn't that much, let's say, science that went into long distance running. So you were naturally talented, you discovered you could run for a long time very quickly, then you would kind of be drafted in to run races, but you would probably have another job, you probably wouldn't have special footwear, let's say, or anything like that, or you probably didn't have a particular diet. You just kind of, turns out you had a bit of a talent for this, and so you just kind of did it. And I think maybe what started to happen from the 70s to the 80s was we began to actually develop shoes, like particular running shoes that actually helped you by maybe making it a bit springy on your step to allow you to conserve energy. Or perhaps you started wearing particular clothes that allowed you to keep cool or keep the right temperature so you weren't too hot or too cold. So those kinds of developments happened around the 70s, 80s. And so what we actually see in the data is it starts to come down again. So we have the initial decrease for the adjustment period. So let's label that. So the adjustment period. Then we have the gap in the 1940s, which, as I've explained, World War II. Then we kind of have this, what seems like a limiting factor in the 70s. So this is sort of the development of, let's say, science and technology, which then allowed it to come down faster. Development of science / tech. Then it starts to come down again, and then it pauses around the 90s. So probably not, this is definitely not to scale, but gives you the idea. So there's a bit of a pause around the 1990s. Let's say that one wasn't there. And then it starts again sort of around the year 2000. And then it starts to come down again, sort of like that. So it looks something kind of like that. So there's a pause here in the 90s. And now what I think has happened here, so whenever there's a pause, that means world records aren't being set. So that suggests that, so obviously here it's because, this is probably because people were distracted. But here, this world record sort of probably held for a while just because this was actually really, really good. And it just, people were still running during the 90s, but they for some reason couldn't get much faster than this one. And so, again, looking back through history and trying to work out what was going on here, it turns out that towards the end of the 90s, maybe the early 2000s, you actually began to see much more money in the sport of marathon running and long distance running. So you began to see here sponsorship of athletes. So sponsorship, and what sponsorship does is it brings in money for the athletes, and it means that they can turn professional. So sponsorship plus professional athletes. And what you mean when you say somebody turns professional in any sort of discipline or job is that they do it for money. They do it to earn a living, and they don't have to do anything else. So what's happening here, when the athletes could become professional, and then we started to see the world record come down. So I think what's happening there is prior to this development, you, as I mentioned, you would have a job. You would go to work, you'd maybe pop out for a run at lunchtime if you could. You'd certainly probably go for a run in the morning, maybe a run in the evening. And you'd fit in your training around your actual work that brought in money that you and your family lived off. Now, once sponsorship came in a big way in the 90s and the early 2000s, you could be paid enough to actually not have to have a job. So your job was to run, you were paid through your sponsors, you probably could employ a coach, probably a nutritionist, maybe some other kind of scientists or the kind of team around you to help you plan exactly, make the most of your talent and maximize your potential. And it became like a full-time job. So I think that shift and that focus to today's athletes, where they spend all day, every day training and running to be able to go faster and faster, break records, win competitions and win prize money. I think that change is probably what's accounting for this slowdown. And then as we started to see things get better again, because you can now train more, you don't get tired from working and other things. So there's actually lots of really interesting features in this graph. As I said, this is just a sketch. You can also see the accurate actual data one, but it has approximately the same shape. So there's loads of really interesting features in the data for this world record. And you'll see this in the world record for most sports and events actually. Perhaps not exactly the same shape, but you'll see that there are certain periods where things go flat. And if you look back through history, you can actually learn what maybe was causing that. Of course, this is all theoretical, but I think if these things tend to line up, it gives you an idea potentially about what was happening. Now, so this is our sort of data and our graph. So what I'm going to do, I'm just going to rub the words off, and I'll maybe just kind of add a few points back on to get the approximate same shape. Because what we want to do with this data now that we've sort of understood where it's come from, which I think is really interesting in itself, is we want to do some actual maths, and we want to try and do a line of best fit. Now, a line of best fit, which you hopefully know from your lessons at school, is going to be a line, a straight line is what we'll start with anyway. A line that goes through the data and it somehow represents what the data points look like. So it's as close to as many of them as possible is how you think about it. So if I were to draw a line like this, for example, that's obviously terrible. The data does not do that. That would be awful. There's clearly a negative correlation, and it's clearly going to be something more like so. Okay, so not that one. That one's bad. That would be a positive correlation. There's clearly a negative correlation. It's decreasing the world record over time. So here's a clean sketch of our data. Again, roughly the same shape as the actual graph that you can see on screen. And what we want to do is try and draw a line of best fit. So I briefly mentioned that the first thing we can do is look for a straight line. So we're looking for a line y equals mx plus c, the equation for a straight line graph, where m here is our gradient and c is our y-intercept. So, and when we're deciding which line to draw, you can kind of do this by eye. So you can, of course, do this more accurately as well, which we will come to. But I can try and do this by eye and say, so if I want this to go through as many points as possible. Now, what you do with your line of best fit, in fact, when you do this properly, and we will use Excel and some computers to do this for us a little bit later. So what it's doing is it minimizes the distance between the line and every single point. Now, when we say it's minimizing the distance, it's actually minimizing the distance squared. Because, for example, if I try and draw one by hand, it might look something like that. Okay, let's suppose that's my line of best fit. It's not too bad. It goes through quite a lot of the points. But now, if you were to take, let's say, a point down here, so let's do this in yellow. If I were to take this point, then the distance is going to be this line here. And from the line to the point is negative, right? So this is a negative distance between the line and the point, because the line is above the point. So line minus point is negative. But if I were to take this line, this one up here, then this distance would be positive. Okay? This one would be positive. So they're on opposite sides of the line. So this one's below the line, this one's above. And so if you were to just take those actual numerical values, so those actual numbers, and when you added them all together, some of them would be plus and some would be minus, and so they'd actually cancel each other out. So you could imagine, let's suppose this one was -1, and this one, it's quite far, so that's maybe +3. So then we have some other numbers, this is like -1 and this one. So say all of these three are -1, and this one's +3. Then if we were to measure the distance between these 4 points, you'd have 3, -1, -1, -1. So the total distance between these 4 points and the line would actually be 0. But clearly when we look, the distance being 0 suggests all of them are on the line. So this point here has distance 0 because it's on the line. But none of these do. But when we add them all together, our total is 0. So that might tell us we could misinterpret that into thinking all 4 of them were perfectly on the line. So what we actually do or what a computer does when fitting a line of best fit for you is it minimizes the distance squared. So it calculates the distance squared, minimizes the distance squared. So it calculates the distance, but then you square them. So here, the total squared, or the total distance squared, I should say, would be 9 plus 1 plus 1 plus 1, and that's going to give me 12. So now we can see that we are actually, all 4 points are away from the line. So when you square them, it removes that change in sign, and it makes sure that what you're actually getting is something representative of whether or not the line passes through those points. So this is what a line of best fit does. It minimizes the distance squared. So as I said, I've tried to just draw this by hand, by drawing my pink line. And in terms of the parameters, if we were figuring this out properly, then the gradient, well, the intercept c, the y-intercept, that's going to be this value up here. So this would be c. And to calculate the gradient, hopefully you all remember that you create a triangle like this. You take this point at value y1, then you say go down, call that x1. Then you take another point, let's say here, which is at x2, and go across to its height at y2. And then your gradient is just given by y1 minus y2 divided by x1 minus x2. And you'll notice here that y1 is bigger than y2 because it's above it, and x1 is less than x2. So this whole thing will actually be negative, which is what we expected because we had a negative correlation or a negative gradient for a line of best fit. So this is all very approximate. As I said, we will calculate exactly what this is in a moment. But I wanted to talk about other possible ideas for lines of best fit. So the straight line, I've kind of covered up most of the data, but we had quite a lot of points up here and down below here that the straight line doesn't go through. And when you look at the graph, it doesn't really look like a straight line. So what you can ask is you can say, well, are there other lines that we can draw that better represents the shape of our data? And it turns out there are, and we're going to consider some of those now. So again, I've drawn out the data, sketched out the data, and also you can see it on screen more accurately. And as I said, what we want to look at here are other types of lines of best fit. So we already looked at the straight line. So that's what we just had a little bit of a think about, and we said, could we take something like that? I mean, it doesn't do a bad job, but there's clearly more, there's more waves. It's a bit wiggly, so it's not perfect. So that one was y equals mx plus c. It's not bad, but maybe we can do better. So then the next thing to try might be the next most complicated expression or the next most complicated graph. And what I mean by that is the next higher order polynomial. So this is an equation in x. We would say it's linear because it has x to the power 1. The next polynomial would be when x is to the power 2, and it would be a quadratic equation. So we could try a quadratic line of best fit. So that, I'll draw it for you in a moment. So a quadratic would be y equals, let's say this was a, x squared plus bx plus c. So these are the quadratic equations that we saw in the first lecture when we were solving for the position of our penalty. Now, a quadratic equation has two possible shapes, really. You can either have the positive quadratic, which looks something like that. So that's when a is positive. And then if I take another colour, we can have the negative quadratic, which looks something a bit more like this. And that's when a is negative. Now, our data certainly doesn't have a hump. It's not a U-shape or a hump shape, but we can actually just take part of that curve to pass through our data. So looking at these two graphs, what we really want here, and I'll draw this on another one, is we could potentially, if we focus on the positive quadratic, then we can just take this part of the graph here. This bit where it's decreasing and curving at the bottom. We can just take this bit of this shape, because if you had that kind of shape, it might fit with our data quite well. So you'll see an example of this shortly, but this is another thing that we could use to try to fit our data. And then the other one, the third one that I want to mention, is going to be a cubic. So the next power of x, so a cubic, and this might be, let's say y is equal to capital A x cubed plus capital B x squared plus capital C x plus D. So you've now got four parameters A, B, C, and D, and a cubic, which you've maybe seen this before, has a kind of wiggly shape like this when A is positive. And again, if you consider A negative, which I'll do in blue, same kind of idea. It comes down, wiggles up, and then goes down like that for A negative. Like with the quadratic equation, where I said we can focus on this curving down part to try and fit our data, we can again just take part of our cubic. And I think again what you're going to be really interested in is either going to be this part as it comes down and goes flat, or if you take the green one instead, you might also be interested in this part. So you've got two options with your cubic. You could try and fit this graph on top of here to create this kind of downwards shape from either these two parts on a cubic or from this part on a quadratic. And for both of these graphs, you can of course experiment with different values of these parameters, A, B, C, or capital A, capital B, capital C, and capital D. As you change those graphs, you can see how the shape of your graph changes. So here with the quadratics, they can become flatter or steeper. They can shift left and right. The cubics, kind of the same thing. They can become slightly flatter. These bumps can either be taller or shrink. And also you can shift left and right by varying all of these parameters. So here's a simple graph that I have constructed in Desmos, and you can all go and do this for yourselves. I strongly recommend that you do to get a feel for how these curves change when we vary our parameters. So here I've got some sliders, and I can just drag these and move them around. So when A is positive, and as it begins to increase, we get a steeper parabola, and as we decrease A, it becomes wider, and once we go to A negative, it then flips to give us the hump shape rather than the U shape. Now, if we do the same with C, that actually just shifts us up or down. So we expected this. C is playing the role of the intercept again, the y-intercept in our equation up here. And then if we were to finally, let's make it quite wide. And then if we were to change B, we can see that it sort of hops around a little bit. So it moves left or right as we change b, and also up or down. And it also changes the shape a little bit, becoming a bit wider in some situations. So we've got 3 parameters that we can vary and get different shaped curves, and we can fix these to get the best fit to our data. And we can do the same here with the cubic equation. So now we have 4 parameters, capital A, capital B, capital C, capital D. We've got these 4 sliders. So when A is positive, we have this upwards pointing cubic, and as it goes negative, you'll see it now points down. As I vary B, we kind of shifts it left and right a little bit, and also extends that second bump. C is going to also shift a little bit those bumps around and change its shape. And D, again, is the intercept. So D plays the role of just shifting the curve up or down. And of course, just like before, we can vary all of these together and get a real wide range of different shaped cubics to best fit our data. If we now take the actual data set, so just the set of numbers, the record and the year, and put it into Excel, what we can do is use the built-in line of best fit feature to actually plot a linear line of best fit. So this one is linear. We can then also calculate the quadratic one, and we can calculate the cubic. So here we have the complete data set. We've got in column A the times, column B the year those world records were set, and even the names of the athletes in column D. And now using this data, we can create a graph as seen here, and you'll see the red line, which I will just double click. So this red line here represents the linear line of best fit that's minimizing the distance squared from the line to each of these individual blue points. So this is our linear line of best fit. We can now over here in the options select polynomial, and you'll see here it has the order. So if we have order 1, it should hopefully, it won't go back to linear because linear is a separate tool. So for polynomial, we have to go a minimum of 2, which is our quadratic curve. And you'll see here, if you compare the linear one to the quadratic I think does a much better job. And then we can increase the power. So here we have our cubic, which again is even closer. You saw that slight shift. If I do that one more time, slight shift there as it kind of shapes a bit more. It's a bit steeper near the beginning. And we can actually keep increasing this to make the line more and more wavy. And you'll see here, the final one we're allowed here is power 6. Now, something you've hopefully spotted from the Excel plots is that as we increase the powers of X that we allow to be in our lines of best fit, as we make the graph curvier and curvier, then what we actually get are more and more accurate lines of best fit. And we can actually take this even further, because to really plot what's happening here and really understand this particular data set, we need something that you haven't yet studied, but I'm going to briefly introduce for you all. This is something you look at A level, which is one of my favorite areas of maths, in fact, the exponential function. So what we really want is to use an exponential function. And the exponential function, don't worry too much about this, as I say, this is definitely extension work, is e to the power x is how we define it. And it's given by 1 plus x squared over 2 plus x cubed over 6 plus ... So what we do is we keep adding powers of x forever. So we actually have, so this is x to the power 0, x to the power 1, x to the power 2, x to the power 3. So we've got all of our cubic terms, but then the next one is x to the power 4, and then x to the power 5. And we keep adding those terms. So we get all possible powers of x. And the graph of this function looks like the following. So it grows big very quickly. So this is when we talk about exponential growth. It looks something like this. So for negative x, it's very small, but as x gets bigger and bigger, this is our y-axis, then y equals e to the x. Looks like this. Now this doesn't match our graph very well. But if we change this slightly and we consider y equals e to the minus x, we actually reflect it to look like this. So this is y equals e to the minus x. And now this shape, to me, looks very good for what's happening with our data set. So this would be a y equals e to the minus x type graph. So what we really want to get the most accurate fit to our data is as many powers of x as possible, which means this exponential function. So here we have an exponential fit for the data, which is given by this grey line coming here through most of the blue data points. So this is a slightly different graph because this is taken from an actual research paper, an actual bit of maths that was published about this world record time set of data. And what we can see from this grey line is it comes down and then we can see it starts to tail off and go flat. So this is the exponential curve that best fits the men's world record for a marathon. So now we've looked at lines of best fit and looked at lots of different type of line of best fit that we could use for this data. What we want to do next is to try and see if we can use those lines of best fit to extend the data into the future. Now this is a very dangerous business, extending things into the future and making predictions. And so you want to make sure it's mathematically sound, first of all, but perhaps most importantly, you want to always remember that any predictions into the future are based on past trends. So we're going to use the past data to try and predict what might happen in the future. Now, the point is we don't know if conditions in the future will be the same as they were in the past. So like I talked about when we first looked at this graph and historically putting it into context, we said that during the 70s, the record was pretty flat. So if we were trying to make a prediction in 1970, we could have very reasonably thought that the record would not go much lower than the rate it was at because the world records were only very, very slowly coming down. And clearly something changed, which as we discussed before, I think was the use of science and technology in running equipment and training methods, and that allowed a change. And then we saw another change actually in the 90s as well, didn't we, with the sponsorship money and professional athletes. So those things, I mean, maybe they could have been predicted, but if we'd made a prediction at any previous point in the past, without knowing those things were going to happen, we would have got a different prediction to what actually did occur. So it's really important to bear this in mind at any time you're trying to make a prediction. All you can do is make a prediction based on what has happened before. If something new happens, we had no idea of having an idea that that would happen, right? So I know I'm stressing this, but it's a really important point about these models. However, saying all of that, we're just going to do it purely mathematically, and we're just going to suppose the exact same trend continues. Can we use our lines of best fit to get some predictions? So we're going to do this accurately using our predictions in Excel, but I'm also just going to sort of roughly show you what's going to happen on the board as well. So for our linear line of best fit, which is our straight line, that's going to look something, again, this is just a guess. Let's say it looked like that. Then we extend it to the future and we get a prediction. Then if we have our quadratic, let's do this one in blue. Quadratic. So we've seen the shape of this is a bit more curved. So it kind of comes in a bit more like this. And so maybe it gets us slightly further. Prediction, again, this is just a sketch. We will do this accurately in a moment. Cubic, let's do that one in yellow. So that was even more kind of curved. It kind of captured the steeper bit better and kind of came in. So maybe that gives us something, I don't know, maybe it's between the two. We'll have to wait and see. And then finally, we have the exponential curve. So let's do this one in white. So the exponential curve, which was the new one that I introduced, where we saw that it actually goes flat. So for the exponential curve, we've probably got something going through most of this data and then kind of going flat. So it could go flat below 2 hours because remember our axis only goes to 2 hours. But either way, something like that. Now I'm aware this is very rough, this is quite messy, it's a sketch, but it gives you a feel for what's going on. So the point is you're going to get these different predictions for these 4 different curves, and then we can compare them and we can perhaps use our own judgment as to which one we think is maybe the best prediction, and you can make up your own minds for yourselves as well. So once again, here is our linear line of best fit, the straight line through the data points, and we can see here that this is giving us a prediction of the world record going below 2 hours for 2005, which of course has not happened, and so I think we can all agree this is not the best prediction. So if we now go over to this panel on the right and we change it to be polynomial, then what you're actually seeing here, interestingly, is that our curve comes down, it fits the data, but then it actually starts to come back up. So if we were to follow this polynomial quadratic fit, this order 2 polynomial, we actually don't get any prediction of when this is going to pass through 2 hours using this best fit parameter of minimizing the distance squared. Now what's going to happen when we go up to cubic? Now for the cubic one, we do get a prediction. This one looks quite good, in fact. Certainly the best of the 3 so far. It's coming down, and then we're seeing it going through all of these points at the end, and then continuing, and I'd say this is around 2040. Somewhere between 2040 and 2045. This would be our prediction based on the cubic or order 3 polynomial fit. We have a prediction here of the men's marathon world record going below 2 hours around 20 years from today. And finally, looking at our exponential curve, the grey line here in this plot, we can see that again, this is going flat before we get to 2 hours. There's this gap here. So just like with the quadratic, this actually predicts purely as a line of best fit that we shouldn't expect the record to go below 2 hours. Now, the other lines on this plot in red, which are here labeled with 1 in 4, 1 in 10, up to 1 in 200. Now, these are actually really important because what these are doing is actually taking our line of best fit, the grey line, which is based on all of the data over the last 100 years. And then these lines, the red lines, actually add some kind of probability or some kind of randomness. So this idea I mentioned about it being very difficult for us to predict the future, we can actually quantify how much we believe in a certain prediction by adding in randomness or adding in probability to our model. And so doing this here, we get the same shape curves, so the red lines are the same shape as the grey, but they're lower down. So the top one is a 1 in 4 chance of happening, the next one is a 1 in 10 chance, down to a 1 in 200 chance. Now the standard in these kinds of models would be to take the 1 in 10 chance, which is why it's shown in bold, and here we can see that looking, it's this second dot, this is around the year 2030 or so, or maybe 2032. So about 10 years from now, according to the exponential model, we would expect the 2-hour world record to be broken in around 10 years with a 1 in 10 chance. So this is actually the best prediction of all of them. Not the best in terms of being the soonest, although it does seem to suggest that, but it's the best from a mathematical perspective because we're actually quantifying our belief in this prediction. Instead of just saying it will happen by this year, we're saying there's a 1 in 10 chance that it will happen within the next 10 years. And that brings us to the end of the second and final lecture on this mathematical modelling in sport mini-series that I've put together for the St John's Inspire programme. I hope you've enjoyed it. I've certainly had a lot of fun explaining these concepts to you. And do remember, please check out my website, tomrocksmaths.com. Also, please subscribe to my YouTube channel, Tom Rocks Maths. There's lots of videos there about all kinds of cool mathematical topics. So if you're looking for things to really get stuck into outside of your schoolwork, then you should find more than enough content to keep you entertained. There will be some follow-up exercises and questions on these lectures, so do have a go at those. So again, thanks for joining me, and best of luck with your studies.